Hello, and welcome to this webinar. My name is Ólafur. I'm a product manager here at Treble, and I will be your host for the session. This webinar will demonstrate the latest features that have been released in Treble or are about to be released. The agenda for today is as follows. I will start by highlighting the reflection tracking feature that was released last month. I will then talk about what we have in store for material creation within Treble. And lastly, I will conclude by talking about what's upcoming later this month and other smaller quality of life features that we have released and you might not have seen. So to start with, I'm going to talk about the reflection tracking feature and demo it. But before I do so, I would like to give you a little bit of a background about what reflection tracking is within Treble. So to begin with, here is an overview of our solvers. So our technology is a hybrid room acoustic simulation setup where we have a wave-based finite element solver that handles the lower frequencies and a geometrical acoustic solver that takes care of the higher frequencies. This is all cloud-based due to the high computing power that we can harness using the cloud, which helps us run wave-based simulations at hitherto unknown speeds. Now, the reflection tracking feature is a visualization of the image source algorithm within Treble. And the image source algorithm is one half of the geometrical acoustic solver, along with the ray radiosity part, or the ray tracer. So what is an image source algorithm? An image source algorithm is an algorithm that traces all of the image sources within a space. And an image source is the deterministic part of the ray solver. That is, we trace a path from a source to a receiver, assuming specular reflections. That is, that the angle of incidence and the reflected angle are the same. It is deterministic in the sense that for a given setup, we know how many paths there are for a specific combinations of a source and a receiver. Now, the image source method in Treble is unique in the sense that it is pressure-based. The ray tracer is energy-based, and the convention is in other tools is that both the image source method and the ray tracer are energy-based. But here at Treble, we decided to implement a pressure-based image source algorithm. The advantage that gives us is that it firstly fits in nicely with the wave solver that we have, which is also pressure-based. It allows us to factor in the angle of incidence when we determine the absorption of a material, and it allows us to enhance the power of impedance modeling of materials. And why is that important? It is important due to the fact that using impedance, you can store both information about the magnitude and the reflected phase of a reflection. Now, the reflection tracking feature, as I say, is a visualization of these image source paths within a simulation. And you can see here on the slide or the image on the left, how image sources are designed or thought out. You can see that it is following, as I said earlier, the Snell's law, basically, where the angle of incidence is the same as the reflected angle. And this is useful in the design stage because it allows you to visualize the assumption that is quite realistic, that the first few reflections are or behave in such a manner. In general, the wave or the reflections become more diffuse, the more reflections or the more often a wave has reflected off a surface. So for the first few reflections, it's a decent approximation in most cases that the image source law holds. And I would now like to go over to the application itself and demonstrate this a little bit with a demo. So here we are within the tool. This is an auditorium that I have set up with multiple sources and receivers. A lot of hard surfaces in here and membrane absorbers, with the exception of the upholstered seating area. And of note is that before you run a simulation, you can go to the advanced settings, and here you can set the image source order that I talked about before, i.e. off of how many surfaces an image source can reflect to be considered valid. Now I've run this simulation with an image source order of 4. So when I go into the result view, I am presented with the traditional result view within the app. But I have now this new component here, which is called reflection tracking. And this is the view that I am met with in there, and I am going to explain it step by step, firstly, and then I'm going to showcase 2 very quick examples of how you can take advantage of it. So first of all, you can see all of the valid image source paths here on the right, and on the left here, you can see the sound pressure level of each individual image source. You can choose if you want to have an unweighted result view or using A filtered results or C filtering. And you can also choose which octave band to look at. And right now we're analyzing the 1000 Hertz octave band results. But you can also use the power sum of all of the octave bands for a single reflection at a time if you prefer to view the total level. So we will keep this for 1000 Hertz for the purposes of this demonstration. Now in here, you can also select a scale, and this scale here governs these arrival time groups here. And this is just meant for convenience sake, so that we have these color-coded groups that depend upon the time of arrival of the reflection relative to the first reflection. So the first reflection is always at 0, and then it is the time after the first reflections when the others arrive that denote where in these groups they fall. If you're designing a studio, you might be interested in the very early part of the sound, so we have a special group for 2 to 15 milliseconds. If you're looking at speeds, you might be interested in a bit later part of the sound field. So that is taken care of with this grouping here. Of note is that you can select which groups to keep in view at all times. So you can select here which groups to have visible and which to hide. So if you're, for example, only interested in what happens after 50 milliseconds or after 80 milliseconds, as is shown here, you can do that. If you select a single reflection, or if you want to do so, you can do that in multiple ways. You can select it off the graph here or the graph here, which I will explain in a little bit. You can also use the arrow keys here or the arrow keys on your keyboard. When a single reflection is selected, you see information about it, the image source order, the sound pressure level relative to the direct sound, the time of arrival, and the time of arrival relative to the direct sound. So how much later than the direct sound does this reflection path arrive? You see the azimuth angle and the elevation angle. I will explain those in a little bit, and then the total distance traveled within the room for that particular reflection. Now, these azimuth and elevation angles denote how the angle of incidence of the reflection relative to the orientation of the receiver. So what do I mean by that? We can see here that I have receiver 1 selected, and I'm looking at the contribution from source 1. This, by the way, can be selected here in the bottom left corner in the info cards. And right now the receiver is facing along the x-axis. I can change that here and make it face along the y-axis, towards the source, or whichever way I choose. But for the purposes of this demonstration, we can keep it along the x-axis. And what you can see here is that this particular hit is arriving at a 90-degree angle in the horizontal plane. And you can see that the highlighted white line here is at 90 degrees. From the horizontal plane, it is almost parallel, so it's only a small elevation angle, and that can be seen here. Now, for convenience, you can also rotate this view here dependent on your viewport. And for example, let's say I have a receiver that is facing towards the source. And if I'm looking at the viewport in this manner here from the top down, I can actually grab this bar here and move this around to correspond with the viewport itself, just for convenience when browsing the results. So what you can also see is that when you select a reflection, you can see how its overall frequency response, so how strong it is at each individual octave band. And you can see that both in terms of the actual sound pressure level and the relative sound pressure level to the direct sound or the first reflection. What is also new is that we also show the impulse response in this view, and we show it in decibels. So this is basically the impulse response in decibels, and it has been normalized so that the highest pressure component, which is usually the direct sound, is 0. And I will go into this a little bit and show you how this can be useful when analyzing results. And I will, in fact, just go over to that now. What I'm going to show you now is a quick demonstration. This is this hole that I've shown you with one modification. I have added this reflector here. As you can see here in the slightly above the states area and slightly in front of it. So what I want to do now is just analyze the effect this reflector has on a particular combination of a source and the receiver. And I am going to look at source 2 and receiver 6 for this demonstration. And if I go here to begin with, in the result view, I can look at the clarity difference between the two. And I can see here that at 1000 Hertz, by adding the reflector, I increase the clarity by almost 2 dB. What I can also see, if I look at this impulse response in decibels, and I zoom in a little bit here, is that this green graph denotes the hole with the reflector. And you can see here that at the early part of the impulse response, I've added a very strong contribution, which explains the higher clarity. So what I can then do is I can go into the reflection tracking view, and I can filter it so that I only see the first 50 milliseconds for clarity. I will look at it now from the side. Let's see here if we can see any difference here on this graph on the left between the two. So now this is the case without the reflector. And then when I add the reflector, you can see this line here that was not there when I didn't have the reflector. I select it, and I can indeed see that I have created a very direct path between the source and the receiver in this case, which increases the clarity of the at the receiver position. Now, I will now look at another case. We go here again and look at the clarity for comparison. What about source 1 and receiver 5? In this case, we can actually see that by adding a reflector, we have decreased the level of clarity at the receiver. And why is that? Well, if we go to the reflection tracking view, we can actually see here, this is without the reflector, and this is with the reflector. And we can immediately see that the reflector is actually blocking the image source path from the ceiling towards the receiver, which explains kind of the lack in clarity in comparison. Now, another quick example that I want to show you is how you can use this to detect flutter echoes in a space. So here I have that set up. So This is a case for demonstration purposes only. This is a very theoretical case. Now, I can now, by the way, remove the side panel here to keep things better in view. There's another new feature. But what you can see here is a 40 meters long room that is 10 meters wide and approximately 3 meters tall. And every single surface has 10% absorption assigned to it flat over the whole frequency range. So what will then happen here is that the sound field is very uniform. The absorption is very evenly distributed. And if we look at the decay curve, for example, we can see that it is very uniform. If we have a single slope behavior, and it is all very nice. The impulse response, if we look at that in decibels, we can see that it behaves quite well. We have a very linear decay. Now, what if we make one crucial change to this setup and change the ceiling so that it doesn't have 10% absorption, but 90% absorption? So we can see it here in this view here. So I've basically taken the surface here, the ceiling, and added a lot of absorption to it. So what will happen is that by doing that, I've basically shut down the vertical sound field, and the horizontal sound field will take over. And what does that mean? If you look at the impulse response in decibels, you can see that the curve is not completely smooth. We have this very prominent sawtooth pattern, i.e. flutter echoes. And that is because we have tuned down the vertical sound field, and then the horizontal sound field will be very strong in comparison. So if you look at then the reflection tracking view itself, and how that can help us analyze this, is that we can see here for the two different cases, without the sawtooth pattern and with the sawtooth pattern. And if we go into the reflection tracking view and track here the reflections, we can see here that the white line on the impulse response graph denotes when in time a certain image source lands on the IR. And we can see here that at these peaks, if I find strong reflection, here is a very strong reflection. And this is indeed in the vertical sound field corresponding nicely to this sawtooth top here. And if I move along, you can see, for example, here we have another top, and you can also see it here. And this again is due to these the horizontal flutter here. So to analyze it further, I've made the third setup with one additional change. So in this setup, I have also 10% absorption at all surfaces, except the ceiling, where I have 90% absorption. But what I've done is I've taken the long sides here and increased the scattering from 0.3 up to 0.9. So I've essentially made them diffuse. I've created a more diffuse sound field, which should then theoretically reduce the flutter echoes. And indeed, when we look at the IR curves in decibels, we can see that we have taken a lot of the sawtooth pattern out when comparing the two curves, but we still see some prominent jutters. And why is that? Well, we can see by selecting one of them here, if I find the top, reflection, we can see that those jutters and those peaks that are still there correspond to the flutter or the echoes that move along the y-axis. And of note is that I have not changed the scattering values of these surfaces here, where this reflection path is moving along, or reflecting off of, rather. So this explains these few tops that we still have, and we can see here for another ones. If we move further along on the impulse response, we can see that this top here corresponds nicely to this reflection path here. So these are just two very brief examples of how you can use reflection tracking during your design to detect flutter echoes, optimize the placement of absorber and receivers, and so on. So now I would like to turn my attention over to material modeling within Treble and what we do there. So first of all, I would like to repeat again that, as I mentioned earlier, the wave solver and the image source algorithm within Treble are pressure-based. And we can therefore take advantage of impedance data. Now, impedance is a material property, rather specific impedance is a material property, but I will not go into those details right now. So this is unlike the practical absorption coefficient that you usually see on datasheets. What do I mean by that? As you know, the absorption coefficient that you see on datasheets from manufacturers is measured in a reverberation chamber, assuming the diffuseness law or the assumption of a completely diffuse room holds. And this is problematic due to the fact that these reverberation chambers are not completely diffuse and cannot be. And there are also problems with the size of the sample, the diffraction of the wave around the sample, and the increased absorption of the edges of the sample, causing all sorts of problems with the measurements, so that you can measure the same material in 10 different chambers and get 10 wildly different absorption coefficients. The absorption coefficients themselves also cannot describe how the phase of a material, or sorry, how the phase of a reflection changes when it reflects off of a material. And that is quite crucial for us to be able to model, because the wave solver solves the wave equation directly. By using reflected phase information, we can accurately model a constructive and deconstructive interference when the wave propagates around the room. So accurate material modeling is important for us, and impedance data is more accurate than the data we can get from absorption coefficients themselves. So what does that mean in practice? This is here a repeat of what I've said. So that means that when you create a new material in Treble in the past using absorption coefficients, which by the way is still an option, we have to reverse engineer the most likely impedance value based on the absorption coefficient that you input. And we have some documentation on how we do that on the website, so I will not go into the details here. But that is a process that can sometimes be difficult for some absorbers. So our material database that we have in the tool, when you select a material and assign a material or assign absorptive characteristics to a surface within Treble, that material database has been set up in such a way that it is using impedance data from analytical solutions. Now, there are two things that we are bringing to the table right now. We are allowing you to import impedance data directly into the tool if you have it. And we are also introducing the beta version of a material builder where you can specify the absorptive construction you have based on its topology. And for the time being, this is a porous material builder only, modeling the normal incidence of sound. And that means, as I will demonstrate in a little bit, that you can, for example, define the absorber as having a certain air gap, certain thickness, certain density. Based on that, we calculate the impedance. The last thing I want to highlight before I showcase this in the tool is this practical absorption coefficient that the material manufacturers show you is based on the chamber measurement method. And I will say there is nothing wrong with these principles per se, and I'm not lashing out at the material manufacturers, far from it. This is established practice for a reason. But these absorption coefficients are not the theoretical diffuse coefficients due to the reasons I mentioned earlier. So the absorption coefficient that we show you in the tool is calculated based on the impedance using the so-called Paris law, which integrates the impedance over all of the incoming angles. And from that, you get an estimation of the random incidence absorption, which is the theoretical absorption for a diffuse set. But without further ado, I would like to show you the changes within the tool itself. So here we are again within the tool. And I will note that this feature will go live on Thursday, so it's not live quite yet. But what you will be met with once you create a new material in Treble is you will still be able to input absorption coefficients like you can do now. But you will see that we have added options here. You can input either surface impedance directly or the reflection coefficient, which is closely related to the impedance. If you have impedance data, you can select dependent on if you have impedance data or specific impedance data. It's, as says here, has been normalized by the characteristic impedance of air. You can either input it as a text file here in this drop-down view here, or you can open it as a text box and copy and paste the values or write them in this box. So to demonstrate, I will import a text file, and note that the data has to be in 1/3 octave bands from 50 to 10,000 hertz. And we will go over this in our documentation, how to best handle cases where you might not have such a broad frequency range available based on, for example, measured data. So if I open here, a case here, and I have some impedance data here, I can now import that, and you can now see that it will show up on the graph here. And then I will calculate the random incidence absorption coefficient based on that data. And you can see that for this case, it went very well. So I will also here explain briefly the target value is the value that you input, these discrete data points here. And the result value is the result of our vector fitting step. So this is also explained on the website, but the wave solver requires a continuous differentiable function as a boundary condition for the materials. So when you input discrete data points such as this, we have to create a continuous function based on that. So this green line shows this continuous function that we have created based on your input data. And also here, for the absorption value, the yellow line is the random incidence absorption calculated based on your input unmodified. The green line is the resulting random incidence absorption coefficient after we have created this continuous function, and that is what the solver actually uses. The geometrical solver, that is, or the ray tracer. The wave solver uses the impedance data here, the green impedance data. Now, you can also import the reflection coefficient, and the process is the same. So I have here now reflection coefficient, and I can input that here, and you can see it comes over here, my input, and I calculate the absorption based on my input and do the fitting, and these are the results. Again, very nice fit, and this is the resulting absorption coefficient. Now, we are also releasing, as I mentioned earlier, a beta version of a material builder. And this first version is what we call a porous material builder. So in this builder, you can define your construction based on the setup rather than the acoustic properties. So you can see here that I can play around with different air gaps. So I can here have 50, or I can have 200. And we can also play around with the thickness of the absorber. For this case, I'm just going to place the absorber right up to the rigid backing. I will leave it as 100 millimeter thick. I can then either specify it or define it in terms of density and wool type, or if I have flow resistivity data, I can input that directly. So if you don't have flow resistivity data, which is not readily available, then this density and wool selection here, based on that, we derive the flow resistivity behind the scenes. So I will keep this as is and start the creation of the material. You can see here that we calculate in the same manner. We create the impedance, the theoretical impedance, based on the models that we used, and those are detailed in our documentation. And then we have to do the fitting process to create a continuous function. That's the green line. And we calculate the impedance, and we also show you the random incidence absorption coefficient resulting from that impedance. Now, it is important to state that for this kind of first version of the builder, this is normal incidence impedance only. And this can be important in some cases, especially when you have a material with a low flow resistivity and a deep air cavity. Then when you set up such a system, you can get a lot of resonances due to the plenum depth. And in those cases, what we do with the materials in our material library is that they have actually been averaged out over different angles of incidence. So it's more than just the normal impedance. For this builder, we are working on that technology to be able to do that in here as well, but we are not quite there yet. And that's one of the main reasons for this being a beta version for now. But the assumption of normal incidence holds the best for materials who are straight up to the rigid backing and have high flow resistivity. Or if there is an air gap, then the air gap is small when compared to the depth of the material. So this will be explained better in the documentation as well. But for now, I would like to highlight these points. So it's important to note. So this is, as shown here, also for porous materials only for now. But we will be expanding on this in the very near future with more types of setups. So for example, we want to do perforated panels and slit absorbers and so on. But we want to get a little bit of feedback from you on kind of how you take advantage of the feature, how you would like to use it, your expectations, and what kind of absorbers you want, so that we can better prioritize what we develop. So we're very excited to hear your feedback and encourage you to try out this version of the material builder, the first version. So don't hesitate to try it out. And if you have any comments on the feature, you can always use the support chat here and submit a feature request. Now, to conclude, I'd like to go over some of the releases that we have released over the last few months that would qualify as quality of life improvements, and we have not put a lot of advertisement behind, but I would like to showcase some of these nonetheless. So the first of it is that within the results view, you can now actually drag and drop the cards here around where you have selected the source and receivers or the different designs to compare to each other. So here I am, for example, looking at the clarity, and let's say I'm looking at 2000 Hertz, and I want to order them so the highest one is the furthest to the left. So now I can just drag the corresponding card to the left, and the color will stay the same or move with the card. So it will not be changed. It's not dependent on the location, but specific to the card itself. And then in this manner, you can customize your setup and your view in a much smoother fashion than previously possible. So another new feature is within this surface receiver view. And what you can do now is that you can select a parameter from this plot here. And you can see how it behaves over the space by selecting or comparing it to a certain value. So you can see, for example, let's say I'm interested to see how much or how big a percentage of this surface receiver has a sound pressure level higher than 84 dBs. And like you see, that is the whole of the receiver. If I increase that to 85 dBs, and like you see, that is only 20% of the receiver. We can also see that how much of the receiver is under a certain value or within a certain range. And you can do this for all of the parameters here, all of the acoustical parameters. So another addition, if I then turn this view off, is that you can now also change the color scale of the surface receivers. And you can do that by clicking on the three dots here. So now you can select between a few options. We have the rainbow is the default one, then Vertis is the second one, and this is a more friendly option for colorblind people. You can also use grayscale if you prefer that, or even inverted grayscale. And you can also use Roma, which is favored within the scientific communities for data scientists due to its nature of not causing kind of the user to see patterns within the color schemes that are not real. So in effect, it has been designed to minimize misunderstanding of the results. So this is one new feature. Then lastly, I would like to highlight that you can now also, this is a beta version, you can click this download icon here, and doing that, you will actually export the heat map that you've created to a PNG file. So right now it is set up in such a way that you orientate your model in the viewport. You can also use this new icon here to orient it whichever way you like to help with that. If let's say you want to see it from a bird's eye view, or even from a slightly inclined view, you download the image or export it to a PNG. And once the download has finished, you can open it and you will be able to see an image that of the heat map as shown on a white background with the legend here for the corresponding view. So this is a work in progress. We would love to hear your feedback on this. We want to create a more kind of robust screenshot view where you can customize parameters such as making the background invisible, save as a specific file format or whatever. We would just love to hear your input on what you would like to do with such a feature before we start designing it. So all feature requests on this and improvements are welcome. So that concludes the webinar. As previously stated, please ask your comments in the field below, and we will now move over to the live Q&A part of the webinar. Thank you very much. Right. We can now start with the Q&A section of the webinar. Thank you very much all involved and taking your time in watching this presentation. I will now go over the questions that we have received, and you can feel free to post more questions here in the chat window below the presentation or below the video. And I hinted or alluded at it earlier in the presentation that I would talk about what's then coming up for new features after this, and I will do that at the end of this session after I've gone through the questions. So let me see here. If I just I'll try to take the questions in order. So I'll take the earliest questions first and then go through it step by step. If I, for some reason, miss anything, then we will post the question and the answer in the description of the video when it goes live. So the first question comes from Anonymous, and it is, will billiard ball reflection visualizations be coming? And the answer to that is yes. There's actually quite a few visualizations improvements that we are kind of both scoping out and working on. Billiard ball reflection being one of them, and it will come. It is not the next visualization improvement that we have in line. I'm not going to spill the beans on what we are actually working on right now, but it involves the wave solver itself actually, and kind of, yeah, you will see when it gets closer to release, but it is a very kind of exciting and much asked feature that allows you to process wave-based information. But billiard ball reflections will be coming at some point. That's no question about that. Then the second question here. Would it be possible to group and display the reflections by their order? So currently the grouping is not set up by reflection order, but that is definitely something that we can add at a later point. And as I mentioned earlier, we are always very open to feature requests. So if we get feature requests about adding this additional grouping step, then that is definitely something that we will consider. When we worked on this, we actually identified quite a few quality of life features that did not make it into the kind of final release, just due to the time constraints we were working under of keeping a good release cadence. And that is something that we will then continuously revisit over the coming months, and this is definitely one of them. Let's see. Then there is a question here. Can you also add receiver near field reflections? I can see it in front of receiver, diffraction kind of thing. So if I understand the question right, then the short answer is that this reflection tracking view is for the specular component of the sound field only. So we're not displaying kind of the diffraction modeling in this view. The way the solvers are set up in Treble is that the wave solver, by solving the wave equation directly, can model diffraction very accurately. I might even be able to show here. We go to the validation cases. I'm going to share my screen here a little bit. See here. I should be able to see my screen. So we have these all various different validation cases here in kind of a controlled environment based on setups that are used to compare different simulation tools. And you can see here how the wave solver fares in modeling diffraction. It can do so very accurately and much more accurately than geometrical solvers. But this view is kind of meant for the display of the specular component only. Stop sharing the screen. Go to the next question. Is it possible to detect flutter echoes with this feature? Yes, you can do that as demonstrated, and we will also be releasing in the future even more features to make that even easier and smoother. Is it possible to obtain the exact coordinates of the reflection point on the wall? We don't display those currently. That is again something we could add. We could make it a downloadable and additional document, because of course we calculate all that data and store it. So it would be possible for us to release it. Again, if we get the feature request for it, it's something we would be very willing to try to incorporate once we again look at the feature. What was the arrow icon in the top right corner of the reflection tracking view? So I go here. Well, I can share my screen. You should be able to see it now. And I didn't touch on this actually, but you can now, so if I go to the reflection tracking view, this arrow icon here, I suppose, is what you're mentioning. Sorry, am I not sharing the screen? Sorry, forgot to press the button here. Now you can see my screen. So I suppose this is the arrow icon you're mentioning. This is new. And you can use this to kind of collapse the side panel now, and you can also collapse the card here below to get a bigger image of or get enlarging the workspace essentially while working in Treble. See. Does the material modeling apply in any analytical model like JCA? So I assume this is with regard to the modeling of the porous material. So we use Mickey's model to model the flow resistivity. That's the model we use. we looked at different models like Komatsu, for example. In the end, this was the Mickey's model. What gave the best result with our fitter, basically. Are all these features included in the base subscription price? Yes, they are. We don't have a tiered subscription, so basically you just subscribe to Treble, and then you have all of the features and all of the parameters that Treble offers. So if I share my screen again, let's share it. Sorry. Then all of these parameters that you can see, all of the acoustical parameters, all of these additional features are included in the subscription. We don't break it down into tiers. So this is the same view for everyone. Then the next question, is there a way to add transmission coefficient to a material? So that's a good question. Currently, we have not added the ability to model transmission, but that is something we kind of have on our roadmap. It is something that we have scoped out internally, both kind of adding transparency to a material so that you can assign a coefficient from 0 to 1, and then a certain percentage of the rays passes through it. And then the next step from that would be transmission coefficient, i.e. the RW value in decibels to kind of or which could be used, for example, if you know the sound insulation of a wall between two rooms, you can do an auralization and hear how it would sound in the other room based on noise in one room. So currently it's not in the tool right now, but I would say that transparency is something that we would want to incorporate in the very near future. How can I get the impedance data? So that's a very good question. It is not readily available. So you basically have to measure a material sample using either a flow resistivity measurement or an impedance tube if you want to get that data. And that's kind of one of the driving motivators behind this material builder, that this kind of impedance data is not readily available. And we want to basically create it for you or analytically model it for you. Will the recording of the presentation be available to watch later? Yes, it will be. It will go live, I think, tomorrow at the latest. Is STI calculation available? Yes, it is. We do STI calculations. Both. Let me see if I can find a good example here. I might not have one open. Want to using here a different setup, sorry, than I'm used to using to show you a surface receiver view. I'm sure that I have open. See here. Yeah, the short answer to the question is yes. STI is included, and you can look at it both kind of on the surface receiver view and see how it is distributed over space. As I showed in the presentation itself, this kind of a target range comparison, you can use that for STI as well and compare it to the different classes. And you can, okay, now I found it. This is not the prettiest example, but it will have to do. We can both see STI kind of visually like this, distributed over space, and then compare it to the classes. And you can also see it on a parameter graph like this. Here. You see again the dimensions of the room it took, for example, a Flutter Echo. So it was 40 meters long, 10 meters wide, and I think I had it at 3.5 meters high rather than 3. It was either 3 or 3.5. I think 3.5. Do you plan to include BIM integration in the future? Yes. We are actually working very hard on that these days. We actually had a round of closed beta the other week, or the beginning of September, where we kind of got a few of our users to try what we have been working on behind the scenes. And we will actually have another closed beta round later this year to kind of get further feedback from our users. So if it is a feature you're interested in and you use IFC files a lot, we would be very glad to, if you would reach out to us, and if you want to kind of be involved in these beta rounds that we are doing to basically make the feature grow and get it to a very good state before we release it. Because we have a very ambitious feature in mind where we want to take in an IFC file and do geometrical simplifications ourselves automatically for you, and then doing making it so that you can assign materials very easily to all of the different layers. So it's a lot of work, and we would be very happy to get more participants in these closed beta rounds. So let me see here. Sorry, I'm going to take a little sip of water here in between. So the next question here. Sorry. This is a great feature, image with a white background and legend. One thing which would make it the feature better would be to have the noise map in 2D as well. Yeah, absolutely. There is a lot of directions to take this kind of a screenshot feature. I think for myself, for example, I would love to be able to have a transparent background and to be able to save in different file formats and all kinds of things. So duly noted, and we will basically cut or store every single one of these feature requests that we get and try to incorporate as many as we possibly can. Can you say something more on the scattering model? Yes, I can do that. Now to try and give a short answer. So the scattering is basically thought in such a way that when you when a ray gets shot out from the source, it lands on a surface, and then the scattering of that surface then determines how it will bounce or be traced off of that surface. So if the scattering coefficient, it ranges from 0 to 1, and if it's 0, then the refraction will be completely specular, meaning that the angle of, or the incident angle will be the same, or the reflected angle will be the same as the incident angle. And if it is 1, then the reflection will be diffuse, or completely diffuse, following Lambert's cosine law, which is a concept that is used by a lot of acoustical modeling tools and is originally based on optics. And this kind of, for example, in the context of the reflection tracking, we and the solver itself, the kind of weighting between the ray tracer and the image source method in the geometrical algorithm depends on the scattering, so that the magnitude of the image source component is 1 minus the scattering. Yeah, 1 minus the scattering. And the magnitude of the ray tracer is the scattering itself. And then when a ray hits a surface, that point becomes what we call a secondary source that is traced back to the receiver. And we use the concept of oblique Lambert in that case. So we use this kind of Lambert directivity pattern, as I mentioned, and we actually align it based on kind of based on the scattering. If the scattering is 1, then you just have the unmodified Lambert directivity balloon. But then if the scattering is less than 1, then the directivity balloon kind of rotates along the specular component. It's a bit tricky to explain it in words, but I can actually say that we are working on some documentation that they'll be quite a lot clearer than what we currently have on this. It's easier to explain this kind of with pictures that show what's actually going on. But thank you for the good question, nonetheless. I hope it, at least what I said, touched on some points. What is the standard to measure impedance of a porous material? So this, let's say the impedance tube measurements or the flow resistivity measurements are the most common. And yeah. So then the next thing here, 2 simple extra features. Introduce parallel view along with perspective one. Download statistics of results, mean, max, mean, standard deviation for point sources. If we start the second point, then absolutely. I think more kind of statistical analysis is something that we will include in the near future. Parallel view, I'm not quite sure I understand parallel view along with the perspective one, but feel free to also send me an email if you want to kind of expand on this. It's op@treble.tech. And then the next question, can we consider a feature that lets users add an absorber or reflector directly into the model? So that's a good question. That is a bit difficult. What we have set up now, kind of the workflow that we have with SketchUp in mind, for example, is that if you have a model in Treble, you set up a simulation, and then you realize, I want to add a panel into the simulation. Then what you can do is you can open the SketchUp plugin in SketchUp, and then there's actually a button there that's called Fetch a Model. And then you can fetch the model, get it from Treble into SketchUp, add the panel, re-upload it, and then when you set up a simulation, you can duplicate the previous simulation. So it will remember all of the surfaces that you assigned previously. So that way you can, that was kind of our solution for this, to be able to better integrate geometrical changes into the workflow, so you don't have to start from scratch every time you want to add a component to this. We will actually be releasing a video about this, like a 1-minute video about this workflow in the next week or 2, maybe in 2 weeks, where you can see, kind of get a better feel for it. But it is also documented, sorry about that, on our website. Is .png download of point source and receiver position possible at present, or just area sources? So right now it's only for the area ones. Maybe, let me see here. Seem to no, you can actually do, exposing my own ignorance here. You can actually, if I share my screen, when you go into these plots here, now I have just the STI plot open, you can actually select the camera icon here, and then you can download the plot as a PNG image. Pause here a few tabs. See. Since all calculations happen in the cloud, is there any way to work with Treble even if I send an NDA with my customer? Yes, I will. What you can do. We actually have very rigid setup on how or what we can do with the data and how we can access it. Because we are what is called SOC 2 compliant. So we can go to this site here that is called trust.treble.tech. And this lists every single kind of security and data handling protocol that we have. And this is actually monitored, not only by us, because it is kind of one of our prime kind of or leading motivations and requirements is kind of safe and respectable handling of data. So yes, you can actually, even though you have signed an NDA with a client, you can be safe in kind of uploading to us and knowing that we won't do anything with that data without your consent and knowledge. And it is much more detailed in here than I can kind of list off the top of my head. So trust.treble.tech is the site you can go to and kind of read about all of the different aspects of our kind of security protocols. Is it possible to export the reflections back to SketchUp or equivalent 3D model? No, that is not within the scope of the feature right now. Again, if we get feature requests for it, then we are very open to explore these avenues. Oh, here's a question I forgot. Is calculation of absorption coefficient with Paris formula for random incidents based on 90 degrees integration of Paris formula? What about the grazing incidents? Yes, it is based on the 90-degree integration of the Paris formula. I misspoke slightly, I think. I will now try to show here and explain briefly what is actually happening within Treble. So, should be able to see my screen now. So in Treble, we calculate the absorption coefficient assuming local reaction. And this is a paper written by Finnur Pind, CEO of Treble. And in this paper, and the reason I bring it up here is because it highlights the different ways to kind of model absorption based on impedance data. And this is basically what the material builder does. It actually uses the reflection coefficient, not the impedance, but it is the same principle since there's a direct relationship between the two. And if you have the normal incidence impedance and assume a local reaction, you have this formula here, and you take kind of the angle of incidence into account with this cosine factor here. And the impedance is a constant here, assuming a local reaction. Then in the material library, as I alluded to, we have kind of something that has been, or impedance that has been averaged out over different incidence angles. And it's not directly this concept here of field incidence, but it is similar in the way that this impedance data that is used in this formula is now not only the normal incidence impedance, but an angle average of over different angles. And again, we have the cosine factor here that takes into account the basically how the waves, or you could intuit it as kind of how much of the wave is going into the material itself. If you have a grazing incidence, this approach is 90, then you get like a minima in the absorption. And then kind of for the future development and the kind of grand future, we would want to have kind of an extended reaction modeling. where the impedance itself is also based on the angle of incidence. So it's not a constant value. So it is these kind of three different methods. It can be the impedance can be based on the normal incidence, it can be on the constant, or it can be an averaged out constant, or it can actually depend on the angle of incidence itself. But in any case, this cosine factor here kind of also takes the angle of incidence into account in a sense. Hope that made it a little bit clearer. Stop sharing again. And then I think I'm down to the last question here. What is the minimum frequency these models, absorption diffusion, are accurate? So the material builder goes down to 50 Hertz. I am not kind of the authority on the validity, how far down in the frequency range it is completely valid. I would have to kind of double check on that from the people who designed it in terms of kind of, I don't want to tell anything wrong right here. If it is as valid as, for example, at 50 Hertz as it is at 125 Hertz, I must admit that I personally am not completely sure about that. But since these are theoretical models, we will put something in the documentation about the feature itself before it goes live to address those questions. It's a very good point. So I think we are through with all of the questions. Thank you very much. I don't think we have had so many questions in a long time. As I say, if you have any further comments or question or clarification, you can email me at op@treble.tech. And now to conclude, I will kind of hint at what is coming, as I promised before. So the kind of next two features that we'll launch are source summing, which is a long-awaited feature, so that you can now look at the impulse response from multiple combinations of sources with a delay setting also. And we're targeting that for this month. And then we're also working on kind of speed improvements for the ray tracer. And we've kind of identified a solution that allows us to run the ray tracer in complicated rooms and complex geometries at an order of magnitude faster speed than has been possible before. And it can handle much more complex geometries like curved surfaces and everything without a problem. So those two are the nearest or two features that will be coming up very soon. And then we're of course working on a bunch of other things that will be rolling out over the next few months. But that concludes this webinar. Thank you very much for your participation, and until next time.